This conference will now be recorded.
So don't say anything stupid.
So we'll wait just a few minutes for people to sign on. And for those that are joining, welcome, and feel free to turn on your camera for introductions if you'd like. We'll do those here shortly, and then we'll get into the presentations.
Hey, Marina and Molly, sorry about the request to present. I thought the share my screen was, or the webcam was share my screen, so I just kept clicking on share my screen, and apparently it sends you a message each time. So I have nothing to present. I'm off the clock for this meeting.
Are you sure?
I'm not even going to present my face. So,
but we would like you to for the intros. No, you don't have to.
I'll turn it on for the intros. Otherwise, I'm going to stay incognito.
Perfect.
That's funny. Yeah. I'm sorry. You're insistently trying to present. Breaking news on the soil moisture realm.
You have enough presentations this week that you probably don't want to do one more.
That's the thing. Yeah. Yeah. I'm happy to listen.
All right, we'll just give it a couple more minutes. I had just sent out a reminder to everyone, so we'll just wait a couple more minutes here. I am not on my game this week, just full disclosure.
So I was just wondering, I guess for many state governments, yesterday was a holiday as well. So yeah. We've got a bunch of people coming in right after the holidays. Okay.
That's all right. We share the recording and everyone can watch it, but we have a few. Chip, Ray, Steve, and Trent are on right now.
Hey Molly, this is Ray. This is the same hour I noticed on my calendar as CPC's drought briefing, which maybe there are a couple folks on there who might otherwise be here.
You know, I just got an email from Dennis that said there are only 5 people on the session, not you or the presenters. Marina, we don't have 2 things going. I'm wondering, well, that is, oh, are they in the Google Meet? Oh, goodness. They're in a Google Meet, I think. Let me jump in there and I will send them the link.
Matthew, are you involved with the NISAR? Are you involved with the NISAR thing at all, or are you involved? You must.
Not personally, but there are quite a few people, in my organization who are involved. But it's a NASA JPL mission. We have some people who are involved in developing products based on, or will be developing products based on NISAR observations, but no one who's really leading any parts of the mission.
Well, then the other question I just wanted to check with you while we're waiting. John Bolton is on the executive committee of the National Coordinated Soil Moisture Monitoring Network, if you've heard of that group. And so you guys are in the same part of NASA, right?
Oh yeah, John is John was in my lab, the hydrological sciences lab. He's still there, so I know. Actually, I hired John, so I know very well.
Great. Okay, well, you did a good job because he's a great asset.
Okay, Marina, yes, people are signing on as there was confusion with that. The Google Meet automatically adds a Google Meet Hangout when you have like over 2 people, and that was something new. So I think that accidentally got left in there. So sorry everyone for that. I'm gonna.
It's okay.
Make sure.
Teams users get the same thing. They throw Teams meetings on top of other meetings just to confuse the issue.
Oh man, I'm gonna send a quick email to everyone that I sent this morning, but just 1 second and then we'll get going. Okay. All right. That is sent out to everyone, so hopefully we'll be good now. Okay, I think we can go ahead and get started. Again, apologies for the confusion on that. We will make sure next time we just have the go-to meeting in there. But welcome everyone to the second webinar focusing on soil moisture products for the Midwest DEWS. We have 2 products this time, GRACE, NASA GRACE product, and also NationalSoilMoisture.com, and we'll hear more about those in a second. But we wanted to quickly just do some introductions so that everyone, I think all the Midwest people know each other, but just so our product developers know who they're speaking to. And if you'd like, you can go ahead and turn on your camera for the introductions, and then we'll all turn them off here as they start to present. So I will just call off names going down the list. I'll go ahead and start with myself. So I am Molly Woolison. I'm with NIDIS, the National Integrated Drought Information System, and I coordinate the Midwest Drought Early Warning System, or DEWS. Marina, do you want to go ahead?
Hi, everybody. My name is Marina Skumanich, and I am a program specialist at NIDIS, staff support to the National Coordinated Soil Moisture Monitoring Network, which I believe you all should be familiar with, at least have heard of, our effort to organize this interagency, interinstitutional effort to create a network of soil moisture network data so that we can get some good products, using the products we've got and also expanding on that.
Great. Audra?
Hi, good morning, everyone. I'm Audra Barushi. I work with the National Weather Service in the Central Regional Operations Center, and I also serve as Central Region's Climate Services Program Manager. So looking forward to the discussions today.
Great. Beth?
Hi, everyone. I'm Beth Hall. I'm the Indiana State climatologist and director of the Midwestern Regional Climate Center.
Hi, I'm Chip Zimmer. I'm with the Kentucky Division of Water. I do all the, or lead the drought monitoring for the state of Kentucky. And I also have my master's in soil science, which is why I really like getting involved with all the soil moisture stuff.
Great. Dennis?
Dennis Toddy, director of the USDA Midwest Climate Hub, used to be a soil moisture monitoring provider in South Dakota, but now only a user.
We are going to skip the developers for now, and I will come back when it's time for your presentations. So I'm going to skip to Jim.
Hi, everybody. I'm Jim DeGrand. I'm at Ohio State University, and I work in the State Climate Office at Ohio State.
Great. Megan? Megan, if you're talking, we cannot hear you.
She just chatted.
Oh, she did. I do not have that open. Okay. Okay, perfect. Thank you, Megan. For those, she is the director, currently serving as the director of the Kentucky Climate Center and state climatologist. Okay, Melissa.
Hi, everyone. I'm Melissa Widhelm. I am Associate Director and Regional Climatologist at the Midwestern Regional Climate Center.
Mike Timlin.
Hi, I'm Mike Timlin. I'm at the Illinois State Water Survey, and I used to be the regional climatologist back when the MRCC was in Illinois.
Good to have you, Mike. Ray.
Ray Wolf with the National Weather Service in Davenport, Iowa. I'm the Science and Operations Officer here.
Steve.
Yeah, hi, Steve Buon, the hydrologist in charge at the National Weather Service North Central River Forecast Center up in Minneapolis.
And Trent.
Yeah, Trent Ford, Illinois State Climatologist, based the State Water Survey here at the University of Illinois.
Wonderful. Thank you, everyone, for joining us. Why don't we, let's quickly have each of the developers just introduce yourself, and then if you want to get into more details of your role, that's just fine when it's time for your presentation. Matt, why don't we go ahead and start with you?
Hi, I'm Matt Riddell. I'm the Acting Deputy Director of Earth Sciences for Hydrosphere, Biosphere, and Geophysics at NASA Goddard Space Flight Center. So sorry for the super long title,
Yeah.
but I oversee an organization of about 400 right now. But I started out as a hydrologist. I'm still a hydrologist, and I'm on the GRACE science team and the GRACE follow-on science team, and I've done a lot with land surface modeling, and I will stop there.
Great, thank you. Zach.
Hi, good morning, everyone. My name is Zach Leeser. I'm a postdoc at Ohio State University working with Stephen Quiring, and I'll be presenting about NationalSoilMoisture.com today. So excited to talk more with everyone.
Great, and last but not least, Ileana. We cannot hear you.
Can you hear me?
Now we can.
Thank you. My name is Ileana Dobreva, and I'm also with NationalSoilMoisture.com at the Ohio State University. I just joined last semester as a postdoc, and I'm working to refactor and improve the code base that generates the soil moisture products, and also to improve the accuracy of the soil moisture products in forests.
Wonderful, thank you. All right, Marina, I will go ahead and turn it over to you.
Okay, great. Well, and I'll be quick. Just want to say to everybody, as you know, we've been organizing this session of reviews of the different soil moisture products that have come to our attention that people are using and know they have value. Wanted to do a little deeper dive in them, and so had the fortune of having the developers come join us and give presentations where we can ask some hard questions. So I hope you have some. As you remember, last month, I guess it was December 14th, we had the first session with NASA Sport List and now CropCasma. This is our second one. We'll be doing a presentation on GRACE and then NationalSoilMoisture.com. And then again, after this, CPC next month and so forth. So we're very excited to have you guys here to present and share information about your tools. So go ahead, Matt, you're first up, GRACE.
Okay, great. Marina, did you say that you just had a presentation on lists? Is that what I heard you say?
Sport lists last month. Mm-hmm.
So like land information system, are we on the same page?
Right, yeah, the NASA Sport List, which provides.
Oh, Sport List, okay, gotcha, okay. All right, so that's interesting to know because the product I'm going to be talking about, can you see my full screen right now?
I cannot.
Let me try sharing again. Share.
There we go.
All right, so how about now? Good?
Looks good.
Okay, great. So yeah, what I was going to say is that the product I'll be describing, it's not actually GRACE. So GRACE is a satellite mission that I'll talk about a little bit, and it makes measurements of the gravity field that we then use to infer changes in total terrestrial water storage. And we use that product as one of the inputs to the product that I'll be describing. On the website where you may have seen it, the website's nasagrace.unl.edu, but that's a little misleading because, again, this is sort of a derived product from GRACE. So the other thing I was going to say is that it's good that you had this prior presentation on the land information system, because our product is an output of a certain flavor of the land information system that we've developed in particular for producing drought products. So let me get into it, just listing my name here, but there are, of course, many authors contributed to what I'm going to show you. Is it going down? Here we go. Okay. So first off, the Gravity Recovery and Climate Experiment, or GRACE, was a mission that launched in 2002, lasted until 2017. NASA and its German partner launched GRACE follow-on in 2018, and that is still active. And what makes this, the GRACE follow-on missions, unique compared with all the other satellite missions that we have in orbit observing the Earth, is that most satellite observations are basically looking down at Earth or looking down at the atmosphere and making measurements using various wavelengths of the EM spectrum, shown in the upper right here. And different wavelengths are useful for inferring different properties of the Earth, but basically you're limited because those you can't penetrate below about a few centimeters below the soil surface. So GRACE and GRACE follow-on are completely different because they're not looking down. Each of them was actually a twin satellite mission. So you have two identical satellites orbiting the Earth, one following the other, about 200 kilometers apart from each other. And every 5 seconds, they're using either a microwave or a laser to make a measurement of the distance between the two satellites with a precision about the size of a red blood cell. So again, 200-kilometer distance, you're measuring that distance every 5 seconds with red blood cell size precision. And what you can do is over the course of a month, and let me move on here, what happens is that as the satellites are orbiting around the Earth, sort of free floating at about a 500-kilometer altitude, when they approach a mass anomaly, which means something like a mountain range where there's more mass. So there's more mass, it means there's more gravitational acceleration. That means it affects the orbits of the satellite. So that first satellite, when it approaches a mountain range, is going to be pulled forward, and the distance or the separation between the two satellites increases. And then as they pass over it, the first satellite sort of held back by that gravitational potential, and the second satellite catches up, and the distance becomes smaller, and then things even out. So so the satellites in that way are sort of sensing gravitational anomalies, but because the measurement is so precise, we can actually make over the course of a month a map of Earth's gravity field, and that gravity field measurement, or gravity field solution, as we called it, is so precise and accurate that from month to month we can see changes in the gravity field. And the reason for those changes is things like mass redistribution. So you think of like ocean tides, atmospheric mass redistribution as there's atmospheric circulation, and then over land, some of the largest changes are changes in terrestrial water storage. So, for example, if you had a big snowstorm, that would be a lot of water piled up on the ground, which translates to a lot of mass and a lot of extra gravitational potential. Not like you could feel it walking around like I feel heavier today, but that it affects the satellite orbits in a way that we can measure. And so again, over the course of a month, we can map Earth's gravity field. We see month-to-month changes in the gravity field. We can use those to infer changes in terrestrial water storage. And going back to this, what's great about that is it is not limited in its depth of penetration. So we can, quote, see things like deep soil moisture and groundwater that you would not be able to measure with any other type of remote sensing technology. So this gives you an idea of what that looks like. So on the top here, we have a time series from Illinois. So Illinois is one of the few places in the world where we have basically co-located measurements of groundwater, soil moisture, and snow, and that's what we plotted here. And you can see this is it's a long time series. The blue is the groundwater, and then on top of that is soil moisture, and then the very top is snow, which is white, and it doesn't have much of an effect in Illinois. But you can see that this is, if you look sort of the top contour of this, that's the change in the total terrestrial water storage. So basically all the water, if you plotted it on the surface and looked at how the height of that water varied over time in response to weather and climate variability, that's what this would look like. And so you can see things like the drought in 1988 and 89, and also the great flooding in the upper Mississippi in 1993. Those stand out in both the groundwater and the soil moisture time series. And this is basically what we're observing with GRACE, is the total terrestrial water storage changes. And so there's a lot of potential here for using these types of observations for drought monitoring. And if you look on the right, you'll see the GRACE total terrestrial water storage anomalies. That's the deviations from the mean. So when it's yellow or red, it's less water than normal. If it's blue, it's more water than normal. And you can see how that compares. I'll play this again if I can. It's not going to play. Let me see. Oh, there we go. So you can see how it compares with the U.S. Drought Monitor for this same time period, which building up to a big drought in the southeastern U.S. So some of the challenges of using the GRACE data are, first of all, it is very low spatial resolution, as you can see by the maps on the left there. You can't really resolve an area smaller than about 100,000 square kilometers. For comparison, the state of Illinois is about 150,000 square kilometers. The temporal resolution is monthly, as I mentioned before, and there's also a data latency of typically 2 to 4 months of the standard product. So they do have these new low latency products, which are still about 2-week latency. And so, that's obviously an issue if you're interested in something like operational drought monitoring. A monthly product that's available, a month or 2 or 3 after real time is going to be difficult to use. There's also a lack of vertical information. So GRACE tells us the anomalies, which is a relative term, anomalies of terrestrial water storage, so relative to the long-term mean, how it varies in time. But it doesn't tell us anything about the components of terrestrial water storage, the groundwater, soil moisture, snow, and surface water. So the reason we even care then, why would we even care all these issues, is again, it has this major advantage that satellite gravimetry is the only technology that's available for global mapping of terrestrial water storage anomalies, or put another way, we can't get any sort of global large-scale measurements of deep soil moisture and groundwater using any other remote sensing technology. And as you know, there are many places in the U.S. where we don't have enough observations, and it's even worse if you look around the world. So what we do is to deal with the challenges I just listed are to basically incorporate the GRACE data into a land surface model, which the land surface model also integrates other high resolution information. So things like observations of precipitation, solar radiation, wind speed, et cetera, that are both combination of observations and atmospheric analyses. So we use the catchment land surface model within the land information system, and we use data assimilation. We use the common smoother type data assimilation to integrate the GRACE observations into the model and basically come up with our best guess of what the actual conditions are. So you start out with a model as your sort of prediction that's a high resolution, and then you have the GRACE observations, which can be used to constrain the model and get better results. So what we've done is we ran the open loop catchment land surface model, so no data assimilation, from 1948 to 2014. We use that as our background in climatology. GRACE was launched in 2002, so from 2002 to present, we assimilate the GRACE data. Also during that period, we use NLS2 as our forcing, as opposed to, for the long period, we're using a Princeton-based forcing meteorological data set. And then the outputs, you know, we have all the water energy cycle typical outputs that you would get from a land surface model. The ones we're focusing on here are shallow groundwater, which is something that the catchment land surface model gets that a lot of land surface models don't. And then root zone and surface soil moisture. In the case of the catchment land surface model, surface soil moisture is roughly 2 centimeters. Root zone is roughly 0 centimeters to a meter. So what we do is we then use the overlapping period between these two simulations, the data simulation, and the open loop. We use that overlapping period to just basically CDF match the climatologies and make sure that they're consistent. And then we can use the long-term record as our background climatology to produce wetness percentiles. So there are a few maps here. Let me show you. Bottom left shows a typical GRACE observation. This is from May of 2014. When we assimilate it into the land surface model, you see we get much higher spatial resolution. That's the 3 maps on the bottom there, the surface soil moisture, root zone soil moisture, and groundwater. In this case, we've converted them to wetness percentiles. So again, relative to the 1948 to present period. And what we've done is, at each location or each pixel within the model, we take that long-term period, we focus on a 7-day moving window, and we compare the current conditions to that long-term record of the same 7-day moving window at the same location to come up with a wetness percentile. So for example, if you're in the 5th wetness percentile, that means it's only been drier than that at this particular location at this particular time of year 5% of the time in our data record. Okay, and these maps have been available. We've been producing these weekly since 2011, and they're posted on the U.S. Drought Monitor, really in the National Drought Mitigation Center website, the nasagrace.unl.edu, and they're one of the inputs that the Drought Monitor authors look at. Okay, so just for fun, here's what it looks like when you animate these. So on the left is root zone soil moisture from the GRACE data assimilation output, and on the right is the shallow groundwater. These are the wetness percentiles again, and you can sort of see how the root zone soil moisture obviously changes much more quickly than groundwater, which has a slower response to the meteorological variations. But you can see things like the development of droughts and pluvials as they sort of move across the land surface. I don't know what I'm doing on time, so I'm going to move ahead here. We've done a lot of evaluations. I'm not going to go through a lot, too many of them, but I'm going to show you here. This is a comparison of our. Let's see what we have here. I think we're just using the groundwater. Yeah, this is just the groundwater versus the U.S. Drought Monitor. So the blue here is the groundwater percentage area across the U.S. In the 5 major drought categories, the D0 to D4, plus all drought categories in the lower right, versus the U.S. Drought Monitor in the red. And so, one thing I'll note right away is that the way we produce our wetness percentiles, they are absolutely constrained to the wetness ranges that we have shown in the lower right, which are the same ones that are used for the U.S. Drought Monitor nominally. Okay, so D0 is wetness range 21 to 30%, for example. But if you look at these time series for the U.S., you can see that the dotted line, the black dotted line, is the percentage of area you would expect to see in that drought category. For example, D0, because it's 21 to 30%, you expect, you've got, it's a 10% range. You'd expect approximately 10% of the country on average is going to be in that drought category at any given time. But you can see the U.S. Drought Monitor is almost always above 10%. And the only time when it's really sort of in line with the percentage is the lower left there, the D4. It's about right. But if you look at the blue time series, the GRACE product, you can see that's pretty close to hugging that line on average. But then if you look at the sort of eyeball the correlation between the two, It's not great for the D0, but the rest of the categories, in particular, all drought categories, you can see it's pretty good. Just want to point out really quickly that we do this at the global scale as well. I think this group is mainly interested in the US, so I won't take too much time on this, but we do have a global drought product that's also available from the same website, as well as from our Goddard stack, which is the lower left there, the disc.gsfc.nasa.gov. Here's some of the requested information. So I think I covered a lot of this. The soil depths that we have in the catchment land surface model are basically 0 to 2 centimeters for surface, 0 to 100 for root zone, and then we have the shallow groundwater, which varies. The downscaling of the GRACE observations is handled by the data assimilation routine. I didn't see what that said in the chat there. Maybe we can ask the question later. Calculating wetness percentages, I think I explained that already. Basically converting to percentiles relative to the same location and time of year based on the 1948 to 2014 open loop simulation, but we've already done matching of the CDFs to make sure the climatologies are consistent. Data blending, the model incorporates GRACE and GRACE follow-on data, but also many other observation and atmospheric analysis based inputs. Frozen soils are handled by the catchment land surface model, and the soil characteristics are one of the parameter inputs for the land surface model. Is that the end there? I'm just going to leave it here with some of the key references describing how these products have been developed. So I can stop there and answer questions if there are any. I saw that there was a few things floated by in the chat, but I didn't really catch them.
Okay, well, thanks very much, Matt. That's interesting, and thank you for the correction. I think it was understood there was a little bit more than just this raw data, but it really does help to have you go through that clearly for us. So Dennis's question is, percentiles in the USDM are not based on spatial percentiles, are they? Question mark. I thought it was based on temporal percentiles at location.
No, they are, but my point is, so if at each location it's a temporal percentile that, you know, any given location you expect that you're going to spend 10% of your time in D0, then if you average over the entire country, you would expect that on average 10% of the country would be in D0 at any given time. I mean, you could do the math to show that that works. And that's what we're sort of showing there is that that for D0, for example, with the US Drought Monitor, they're usually over 10% of the country in D0, which means that they're not sticking with that temporal percentage at any given location.
Dennis, did you want to comment on that or respond?
No, not right now.
Okay, but that's really an interesting observation. Have you shared that more broadly, Matt, with USDM folks?
I think they're aware of that, and it comes down to them trying to be careful about, you know, not underestimating drought extent because they know it's so important for policy decisions. They try to avoid the political pressures, but sometimes it's unavoidable. You want to be careful. So I'll leave it at that. I don't want to try to speak for them.
We'll mark it as your personal opinion, you know, as opposed to official. Okay. Any other questions for Matt? If you want to, you can either type them in the chat or unmute yourself.
I want to give a shout out to Chip with that Hartford Whalers shirt. That was my team when I was growing up in Connecticut until they got stolen away by Carolina.
Could I may have missed this, sorry. When you mention your root zone and the different levels, what do those are supposed to correspond to? What are the actual levels those are supposed to correspond to?
Yeah, so the surface soil moisture in the catchment land surface model is roughly 0 to 2 centimeters, and the root zone soil moisture is roughly 0 to 100 centimeters. And then the shallow groundwater, it varies by location. Does that answer your question?
Yeah, does that work well all across the country?
You know, there are definitely simplifications in the model, and that's one of them. And in fact, in a way, I'm oversimplifying the way the catchment land surface model works, because it's quite a bit different from other models that typically have something like 4 layers. And the catchment land surface model is doing something where it sort of defines the what it calls the catchment deficit, which shows how the basically the moisture profile in the soil, and then it's got this root zone excess and surface excess. So if you want to read about the catchment land surface model, I don't, you know, it's kind of a lot to get into right now, but to answer your question, yeah, it's one of those simplifications that works well in some instances and not in others, but you know, in general, it works okay. It's actually more of an issue with the groundwater. The original parameterization in the catchment LSM really oversimplified the depth to groundwater, and we had to make some changes to make it work in our product.
Hey, this is Trent. I have a quick question. The sport list model, and I know this is much different than that in many ways, but when comparing the last few months and comparing the sport list model to the GRACE root zone soil moisture product, at least in Illinois, and again anecdotally, sort of not necessarily super quantitatively, the GRACE product has in my mind is kind of better mapped onto our in situ observations, and is in general dries down a lot more slowly than the sport list model tends to. And I was wondering, I mean, do you have any explanation for that? I mean, is it, you know, is assimilating terrestrial water storage, including that root zone soil moisture from GRACE, is that something that can maybe give us a better idea of root zone versus assimilating something like SMAP, which is just the surface? Or I mean, any ideas or thoughts about that?
Yeah, I'll do my best there. So Trent, first of all, thanks for your reviews for Journal of Hydrometeorology. I think you've done a couple for me. But so I think the list sport uses the NOAA land surface model, if I'm not wrong. So first of all, we got that difference. You got the NOAA land surface model versus the catchment land surface model, and they're going to act somewhat differently. I do think that GRACE data assimilation has a significant effect, particularly what you were talking about. It sort of observes a lot of the lower frequency variability in terrestrial water storage. You know, as I said before, the groundwater changes pretty slowly. You know, and obviously deep soil moisture changes more slowly than surface soil moisture, and so you're getting sort of more of that in the GRACE data assimilation sort of applies that constraint. And it sounds like it's working well in Illinois, which is great. The funny thing is sometimes it actually makes things not work as well because the groundwater variations tend to sometimes slow down variations in the root zone soil moisture. And there are some places where you want those variations to happen faster. So I'm glad to hear it's working well in Illinois. Hope that answers your question.
Yeah, thank you.
Matt, on that score, can you characterize, roughly speaking, where those places might be? Would it be sort of the drier southwest, where you expect a faster drawdown or something?
Well, I would say it's areas where there's a deep water table. So, for example, you know, over the high plains aquifer, you can have, you know, very deep water table, you know, tens or even 100 meters. And GRACE is still observing those water table changes, and then the model is not, the catchment land surface model is not really set up for simulating groundwater that's that deep. So it places the groundwater in the model closer to the surface. Maybe it's only, you know, 10 meters from the surface when it should be 50 meters from the surface, and therefore it ends up affecting the root zone. And so you get, you know, changes in the root zone that happen perhaps more slowly than they should, because that groundwater is interacting with it when really it shouldn't be, because the groundwater is much deeper. So to answer your question, I'd say places where there's a deep water table, there may be issues with the soil moisture in our data assimilation output not responding quite as quickly to the atmospheric phenomena as it should. But if you have a shallow water table, then we're in good shape. and Illinois is pretty shallow.
Yeah, that's great. Well, that's the kind of details that's so valuable, because obviously no product's going to be perfect everywhere. I mean, I don't think we should expect that. And so just kind of having a sense of where things do work well and where maybe to look at something else to have a double check is very valuable. Any other questions? I know I have one for you, which others may well know, but the maps are provided on the UNL website. Are they partners in this research, or is it because of the connection to the USDM?
Yeah, no, they were. So we had an original proposal funded back in, I think, 2008 to start doing this work, the GRACE data assimilation and producing drought products, and our partners included Brian Wardlow and Mark Svoboda, and they've been partners with us ever since. Our most recent funded project has since ended, but you know, we still consider them partners because they're delivering the products for us, and they do a great job. They were very responsive when there were issues and that sort of thing.
Great, great. And then another question I had is, what's on the horizon? Is this pretty much, I mean, I know it's a stable, established product, but are you guys thinking about enhancements, or have you moved on to some other things?
We'd like to at some point begin to offer basically a twin product where we use the NOAA land surface model instead of catchment. That's one thing. We also have something called our Western Land Data Assimilation System, which, you know, there's a North American Land Data Assimilation System, there's a global LDAS, and so we've developed this Western LDAS, which is a 1 kilometer resolution system, and we'll be incorporating GRACE data assimilation. And we partnered with folks both in California and Colorado, including the state climatologists there. So that's a new product that once we've got all the kinks worked out, will be nice because it's got this very high spatial resolution.
Right. Okay. All right, last call for questions. Okay, well, Matt, thank you very much. That's really interesting and very helpful. And I really do appreciate all the references, et cetera. We're going to be compiling that in a list, by the way, folks, so that we can keep, sort of keep those handy as well. So again, thank you for that presentation. And I'm going to now call up Zach Lisa for the second part. Let me go ahead, Zach. I'm going to give you, I think I've just given you, here we go.
Great.
All right, you can see that just fine.
Perfect. So you can see my screen?
Perfect. Yep. Go ahead.
Okay, thank you. Yeah, and I want to thank Molly and Marina for including NationalSoilMoisture.com in this product review. These have been really informative so far. So I'm excited to talk about NationalSoilMoisture.com today and building a national soil moisture data set. Before I get started, I definitely want to acknowledge all of my colleagues who are currently working on this project. Stephen Quiring at Ohio State, who couldn't make it today, he's teaching class. Ileana Dobreva, also at Ohio State, and Trent Ford at the University of Illinois. And I know Ileana and Trent are also on the call today. And just to kind of expand upon my introduction, I started working on NationalSoilMoisture.com as a research assistant when completing my PhD with Stephen and Trent leading a team at OSU, and have continued working on this, and especially as we're getting more into less developing the website and more looking at some research questions we can answer with these national soil moisture data sets. And so just for a little bit of background here, the goal of this project is to develop a national scale drought monitoring product that integrates multiple diverse sources of soil moisture information that can improve drought monitoring activities and drought early warning. So this project originally started in 2018, and it was funded by a NOAA map proposal. And so the original work really was getting things running, developing and deploying a series of national soil moisture products that were based on in situ measurements, remote sensing data from the NASA Soil Moisture Active Passive mission, and land surface models from the National Land Data Assimilation System. So these products are now operational and provided in near real time on the website. And where we're currently at is working with NIDIS funding to continue to improve the website and the cyber infrastructure, but also support a broad range of projects that focus on the applications of national soil moisture data. And so one thing I wanted to start with is this is from our homepage of the website, and it's really the backbone of NationalSoilMoisture.com. And this is all of the soil moisture data that we're currently aware of and working with in the United States. So each point represents one of approximately 2,100 in situ stations across the United States, and these come from 24 different state and federal climate monitoring networks. And these stations that provide in situ measurements of soil moisture really help to inform a lot of operational products that we make available at NationalSoilMoisture.com. So this table here is kind of a summary, and all products listed here are updated daily on a 4-kilometer grid. And so based on the in situ data, we have an interpolated map of soil moisture that goes out each day, and this is at a 1-day latency. So that means if you visit the website, if you see a map using the regression Kriging interpolation, this is showing yesterday's soil moisture data. And so this regression Kriging interpolation produces a soil moisture estimate at 5, 20, and 50 centimeter depths. And for all data products, we try and standardize the soil moisture as volumetric water content percentiles. And we do this because, again, we want to inform drought monitoring activities. So it's better to display the soil moisture as relative wetness and dryness rather than just the volumetric water content. And so we also pull in the model and remote sensing data. So the model data from NLDES, we use the NOAA land surface model. And this brings our latency actually to 5 days of being able to update on the website. And this is really just a function of being able to download the NLDES data. We're using the model output using the NAR reanalysis forcing data. So we kind of have to wait on the latency to update that. But then we take the initial NLDES data that's at the 8th degree resolution and kind of downscale it using a cubic spline interpolation down to that 4-kilometer grid cell level and display that as well. We use the NASA SMAP level 3 data, which provides soil moisture, and we match that latency to update with the NLDES. This is originally at a 9-kilometer resolution, and because it's not a spatially continuous product, that we use just the nearest neighbor downscaling to get that down to 4 kilometers. We also pull in and display PRISM 7-day precipitation, and this is used in that regression Kriging to improve our gridded estimate of the in situ soil moisture. And finally, based on all of this data that's displayed on the website, we also have derived products. So blends of in situ model and remote sensing soil moisture and on some uncertainty metrics as well. So we have a blend using all 3 sources and then a blend that's just based on the in situ and model data as well. So these are the products that are produced. And I won't go through this slide in detail, but I just wanted to give an idea of kind of what's going on behind the scenes within the cyber infrastructure to kind of pull in this data and operate in near real time. And so first, when we first started, we really needed to target our networks and download all of the historical data. But now to run operationally, we're running code that pulls soil moisture each day just to get one measurement from all of our sources and stations. And then we run it through a quality control algorithm. And this is pretty important. If you want to get into the details, I've listed some references here. But really, we just want to remove erroneous measurements, fill in missing data where we can, and then standardize those measurements to some common depths to easier display them on the website. So once it's run through quality control, the soil moisture data, we then calculate the soil moisture percentiles at each depth. And we do that then to be able to interpolate and aggregate these data products since they've been standardized. And that's kind of what goes into generating the daily soil moisture maps each day. And so this is running operationally, but in collecting all of this soil moisture data, we really are also building a historical database of soil moisture across the continental United States. And so just to give an idea, these time series plots here show the number of stations from which we have acquired data from 1996 to 2018 when we started collecting data more operationally. And so you can see it really starts in the late 90s, really with just the Oklahoma Mesonet and the SCAN network, but we've really gradually increase the amount of stations with soil moisture sensors in the United States. And so these data are converted along the way. So the black line shows kind of raw data that you can pull in. But as we run it through quality control and calculate percentiles, you do lose some of the data, which kind of reflects in that period of record as well. And so while I originally showed 2,100 stations that we were targeting, the historical data so far, we only have for roughly 1,400, 1,500 stations from 19 of those networks. And that's because as new data becomes available, new networks and sensors come online, we need to ensure there's a long enough period to calculate percentiles, standardize that data, and we're also still kind of working through adding some of these new networks as well. So future and current work is really trying to fill in some of those gaps from 2018 to present and add more data. So that's kind of an overview of what's included in the historical data. But I definitely wanted to mention today that really in the past year, we've made these historical data available upon request. And so right now we've got a couple different formats that the data is organized for, depending on how you want to slice up the data. The first is just you can get the data as a time series for any station or network that you're interested in. And we make sure that these are networks that are okay with the data being redistributed. But these data have been run through our quality control algorithm and then made available as VWC or VWC percentiles. To calculate those percentiles, we really try and use the full period of record, so as much data for each station as we can. So we just use an empirical CDF and then use kind of monthly discrete windows to calculate the percentiles for that location. And that's really to kind of speed things up operationally. And we make sure that there's at least 100 observations in those monthly windows for a station for the percentiles to actually be calculated. But we also have these data organized as more of a national data set. And so these would be daily files where it would list all available soil moisture measurements on that day and as part of one of 3 depths, so 5, 20, and 50 centimeters. Obviously, all of the sensors aren't measuring at these depths across the country. So in some cases, we make some proxy assumptions and move measurements around to do so. So this historical data set was built for the website and built for drought monitoring. But one thing we've found is that it's also very invaluable for scientific research to kind of pull all these data sets together. And because of that, as I mentioned, over the past year, we've started to work with others and share these data with people working at NOAA, USGS, NCEI, also university researchers. Right now, the data is just available as raster maps or CSV files. We're hoping to kind of improve our data delivery this year, maybe making some more accessible data formats such as NetCDFs. But I wanted to mention, if you're interested in learning more about these data products or accessing them, feel free to contact us. I'll list our information at the end. But the most important thing I've found from working with others is getting feedback. And we really appreciate your feedback, whether it's finding some errors in the data set or some suggestions to improve how it's organized. That's really helpful on our end. And so the historical data right now is largely station-based, but we've got some work going right now to develop historical gridded products. So looking at the regression kriging and pulling that back in time with the station data as well, and then working to get an API set up for easier data delivery, especially with some of these larger gridded data sets. But as I mentioned, as we're sharing this, we're learning that these data can be used to answer a lot of important science questions, but then research using National Soil Moisture products also then helps to kind of re-inform what's going on at an operational level. So here's an example of some kind of research based on the data that's collected at NationalSoilMoisture.com. And this is an assessment of station quality for a large group of stations that's on the website. And so this is a triple co-location analysis that kind of looks at each station and characterizes the total error of the in situ measurements with respect to some independent data sets. So here we use the NLDES as a model data set, and then the European Space Agency CCI satellite as kind of a remote sensing product. And so what this is looking at is the spatial representativeness or the spatial footprint of that in situ measurement. And so how does it relate to some other products at a more coarse resolution or gridded product as well? And so what these box plots are showing here are the random anomaly error or RAE values. And really what we want to look at it is the RAE shows which stations correlate well with the other data and might be spatially representative. So there are some outliers, but really what we're looking at are some of the lower RAE values that show what networks and depths those measurements are representative of larger scale products. And so an important finding from this study is that approximately 95% of 1,200 stations used had low measurement error and high spatial representativeness. So these may be good for including in some derived combined products. And so we can also look at these broken down geographically as well. And so maps such as these are helpful to highlight where in situ data is not matching other products. And this could be due to a variety of physiographic characteristics or maybe identify locations where we might need a denser network of stations. So this research has been important, and it's helped to inform us about the quality of our stations as that they're being combined with other products as well. And so I've mentioned these blended products, and right now on the website, we use a equal weighting approach just to combine either 2 or 3 products. And so this is a paper based in 2021 that really looked at different ways to weight different types of soil moisture when combining them. So what these box plots are showing are the error when using different methods, whether it's weighting the stations and products based on their triple co-location data, a least squares weighting, or just the equal weighting. And really what was found is that just a simple average, it really outperforms some of these other methods when you do a kind of a cross-validation analysis on these data. And the maps here show that, especially looking at panels F and H here, that average approach really does a good job of capturing the soil moisture patterns in the south central US. And so this has helped to inform us on the website of how to consider blending these data and also considering the uncertainty as well. And so here's an example of combining different sources, and this is just for one day, but we can go on the top left, it's the NLDES data, top right, it's the in situ regression kriging, and then the SMAP in the lower right, which isn't continuous across the whole US. And so what we see on the lower left is kind of a combination of the 3 of them, and then the points on the map show the stations percentiles, and then the map shading is the percentiles at the grid cell. And so this is interesting to see because overall there's actually quite a bit of agreement where the station data that originally went into the regression kriging is also agreeing pretty well with the blends, but that's not always the case, and so that can be useful to look at. And so as we've kind of started collecting these blends in near real time, we have a bit of an archive to start looking at some of the uncertainty that comes with these. And so this could hopefully spark interest in some future research projects that want to expand upon this. But this map, for example, shows the annual mean daily 5 centimeter uncertainty for all of 2020. And so there are some areas in the US where the 3 products don't really agree. It's maybe where we would expect in the Intermountain West with really variable topography. But then across most of the southern US, there is quite a bit of agreement between the 3 products. There's really a mean uncertainty of 0.1 to 0.2 percentiles. So that's interesting to see. And as we continue to collect these data, we can use applications such as this. And so I've highlighted some applications for soil climate analysis, but national soil moisture data sets can also be used for more interdisciplinary applications as well. So here's just a few examples where some of these data have been used to predict crop yield, predict power outages for utility companies, used in weather forecasting and stream flow forecasting as well. So there really is a broad range of applications. And so where are we right now and what are the next steps? I'll just kind of quickly go through these. We're currently working on and kind of continually working on really improving the uptime of the website and increasing the number of data sets that we're including in these products. As we're doing so, we're trying to keep a lot of documentation to develop Mesonet metadata that provides kind of a comprehensive description of all of the data sets and access to those through the website. but there's also some more research applications that we're starting to work on. So Ileana's here, and she started to work on a project with the U.S. Forest Service that's looking at validating and improving the accuracy of soil moisture in forested areas. And this has become a more prominent research topic over the last 5 years or so, and assessing, how do different soil moisture data types perform in these forested environments. And that's also introduced us to a few other networks that we hope to include in the future. As I mentioned, we also want to improve the uncertainty. Right now, it's a pretty simple product that's just looking at the difference between input data sets. But ultimately, what's driving the uncertainty? Is it the station density, the spatial representativeness, or is it the data quality? These are important research questions, and we hope to look into them further and hopefully deploy more complex and useful uncertainty quantification products on the website. Another thing we hope to do soon is led by Trent, and that's to help develop a soil moisture based flash drought early warning product. So on the website, this could show projected changes in soil moisture, but also how that's triggering a rapid drying could trigger flash drought conditions. So looking at synoptic conditions as well, and making predictions that could accompany the near real-time data on the website so far. And finally, a newer research project funded by USDA will hope to downscale some of these soil moisture data a little bit further, maybe to the field scale level, by using machine learning with some other hydroclimatic variables such as evapotranspiration that relate to soil moisture. So that's kind of a summary of our next steps. And I want to end the presentation here, and I'm looking forward to kind of some questions and answers. But before we do that, I want to acknowledge some others who I didn't mention at the beginning who have helped a lot with this project along the way. And I also want to acknowledge both previous and current funding sources for keeping NationalSoilMoisture.com going. And so here's our contact information if you want to know more about the data or request some data. And finally, I wanted to include everything I've talked about. Here's some selected publications, but these are also listed on the website. So if you want to learn more about any of the methods, those are available there. So with that, I'll go ahead and in the talk, and I'm open for questions.
Wowee, Zach. That's a lot. You guys are doing a lot of good stuff. It's really exciting. Any questions? There are a lot of different pieces there. Go ahead and either put it in the chat or feel free to unmute yourself. I know I had one question, and again, I may be the only one who is confused or wonders about this. With your triple collocation comparison study, it sounded like concluded, at least what I heard was concluded, that there may be some areas where there needs to be more density, or there's some question about the in situ measurements. But in that case, how do we decide what do we really consider the baseline? I mean, could it also be that the models just poorly estimating numbers, of soil moisture values in that particular area, or same with the satellites sort of missing it? How do we sort of tease out where we really focus in terms of what needs to be improved?
That's a great question, and that kind of motivates the use of triple collocation. And I know Trent can speak more on this, but really, yeah, we don't know the ground truth of soil moisture at any location. There's going to be bias with in situ measurements, models, remote sensing products, especially when doing an analysis at a national scale. There's also regional biases as well. So that's why that triple collocation methodology was used, and that instead of assuming one product is kind of the superior data source and is the real ground truth soil moisture, it looks at kind of the variability of the data with relation to each other, and to try and hone in on how does in situ vary relative to others, not necessarily relative towards like a cross validation of maybe a ground truth that we're considering the actual soil moisture measurement. So hopefully that kind of answers it, but that's the strength of that methodology.
Yeah, okay. It sort of answers it, right? It's still a little confusing, but kind of like being on ice floes. You don't really know where the ground, yeah, as you said, where is the ground? Okay, Mark, Brian Mark has a question in the chat. Who is making most use of the product?
Great question. And I'm glad I have this slide up right now because this shows some of the research that's been done involving the national soil moisture data. And I would say up until recently, it's been mainly university research. And so it's been university researchers that are looking at some of these science questions and benefiting from having not just data from one or two networks, but more of a national composite data set. But again, we're hoping to maybe, as we improve the website and make these products available, working more with government agencies and more operational climate analysis to kind of inform them with some of these soil moisture data products.
Any other questions? I did want to mention to folks that we are actually, NIDIS has been sponsoring this work for a while, along with some other groups, and we're actually working now on a plan to transition this marvelous research activity to a government platform so that it can live long and prosper while these researchers have a chance to go off and do science, do more different science. So stay tuned for that, everyone. I know it's a little bit confusing. The NationalSoilMoisture.com is obviously a commercial site, but it's hosted by the university, but then we'll be transitioning to some sort of .gov. We're working on that this next year, so next couple of years maybe. Yeah.
Yes, and we're definitely looking forward to that.
Yeah, and I'm sorry, Zach, you may have mentioned this, and I apologize, I didn't catch it, but is the historical data is up now, available?
Yes, so those station-based data sets are available upon request. We'll try and set up a way to share the data if you can just reach out via email. But really over the next few months, we want to get an API set up because we're finishing up getting some more gridded data sets available historically. Those are a lot larger and not as easy to distribute. So hopefully, this kind of academic semester, we can get an API set up where it's easier and you don't have to make a data request. But for now, just reach out to us and we're happy to provide some documentation and share the data.
Great. Yeah. Okay, we've got a question for you, Ileana.
Yes. So the question is, if I can talk some about improving measurements in forested areas. And what I can share is that my focus last semester was developing scripts that I can access the data. So for example, being able to access the specific grids of interest given a latitude and longitude, and also being able to pull in-situ information given a list of stations. So I haven't done any analysis yet to compare the different soil moisture measurements in forested areas, and this is what I'm going to be focusing on this semester. I also looked at the NEON infrastructure. They have a list of stations which we have not included yet in the National Soil Moisture Network. So I'll be using data from NEON as well. And one of the things that I'm interested in is using remote sensing data that identifies forest characteristics, and then using the forest characteristics as information for improving the soil moisture. And this is assuming that, say, for example, if you have more or less dense forested areas, this probably affects how soil moisture is measured. So long story short, this is going to be my focus this semester.
Great, thank you. I was just curious to hear more of where things were at with that. I know, like Zach, you said earlier, that definitely has been an important effort and of the last year has gotten a lot of attention of the representation of soil moisture in forests. So
yeah,
it's really
my previous experience that relates to this work is I worked on using remote sensing to estimate snow cover fraction within MODIS pixels. And so in a sense, what I did is I used Landsat to create the training data that I then used to train a neural network to estimate the snow fraction within the much larger MODIS pixels. And one of the topics related was that forests, when we work with optical remote sensing, forests may hide the ground, so it is more difficult to estimate the snow cover in forested areas. So when I start the analysis of improving soil moisture in forested areas, I'll be informed with that perspective. And that's why I'm interested in using forest information such as density or type, whether it's evergreen or deciduous. And of course, then seasonality would be important if we are looking at soil moisture in deciduous forests. Okay, thank you.
Great. And with this work, will you all be ending up with a new layer at NationalSoilMoisture.com, or will it actually be blended in with the other in situ? Will it be sort of integrated into the in situ maps? Do you have a sense yet, or is it too early to know?
I would love to see a new product where I would love to see a new layer, but this may be just because I want to create a new layer. But I don't know what the needs of the community are yet. So I'm just going to focus on what is necessary to be accomplished.
Okay, great. Well, and those of you on the call, if you heard that invitation, if you have an opinion on a separate layer or integrated, that would be great. Okay. Any other questions? We're going to also invite people, if afterwards you think of something, we'll also be pulling together questions and sending to the producers, developers, if we have them. In the meantime, though, we may be at the end of the session. More questions coming up. Well, okay, thanks very much, Zach and Ileana and Matt earlier today. This is really valuable stuff, and particularly now that we've recorded, I think it will be of value to others to watch and have a better sense of these different products. And really a lot of good information shared today, so appreciate your time.
Great, thanks again for having us.
Okay, Molly, well, shall we just say?
Wrap up, yep. Thanks again, everyone. And if you do have any other questions, definitely let us know and we can pass them along and get the answers to everyone. Later today or tomorrow, I will send out the recording, the notes, and also the slides. So yeah, thank you so much.
And don't forget, the next session is February 9th, and we'll be talking, working through the CPC soil moisture products.
All right. Thanks, everyone. Have a great day.
Bye-bye.